Now we will discuss how to realize a voltage controlled voltage source with gain 1 or a voltage buffer using a MOS transistor. The output voltage should be equal to the input voltage. Now a MOS transistor looks like this, and what we are thinking of is to use just a single MOS transistor to realize this voltage buffer or a voltage controlled voltage source. Okay. Now MOS transistor compares the gate voltage to the source voltage. That is, it takes the gate source voltage and multiplies it by a certain constant Gm to produce the drain current. Okay. So the current depends on how much the gate voltage is in comparison with the source voltage. So we can think of it as comparing the gate voltage to the source voltage. Okay. Now what do we want from a voltage buffer? V0 must be equal to Vi eventually, right? Now if Vi is greater than V0, then V0 must be pushed up, it must be increased. And how do you do that? How do you increase a voltage? This means that current must be pushed into the output node. Okay. And of course, if Vi is less than V0, exactly the opposite must happen. V0 must be pulled down, or current must be pulled out of the output node. Okay. Now what really happens in a MOS transistor? If VGS is greater than 0, then this current flows from drain to source, and you can see that the current is pushed into the source node. Okay. And similarly, if VGS is less than 0, current is pulled out of the source node. So how can we arrange these voltages so that this action happens? Remember, V0 is the output voltage. Okay. So output voltage must be part of the comparison. What I mean is, we are comparing the input voltage to the output voltage. So VGS must be either Vi minus V0 or V0 minus Vi. Okay, any of these things is possible. VGS is comparing the gate voltage to the source voltage, so it must be whatever we want to compare. It could be Vi minus V0 or V0 minus Vi. Okay. When Vi minus V0 is more than 0, then current must be pushed into the output node. Okay. And here you see that if VGS is greater than 0, current is pushed into the source of the MOS transistor. Okay. You can try out different combinations, but it appears like if you apply the input voltage here, if you think of the source node as the output, then what gets applied as gate source voltage is nothing but Vi minus V0. Okay. And also, if Vi minus V0 is greater than 0, then this current is flowing downwards into the source node and it's pushing up the source voltage. Okay. It is pushing a current into the source node and it increases the source voltage, and it's exactly the condition that you want. Okay. So this is how we use the transistor in negative feedback. Now I already knew what the topology must look like, so I considered only this combination, but you can try the other way around. Now I took the output from the source, so instead of that you could try taking it from the drain node. Then you will find that you cannot arrange this negative feedback in a convenient way. Okay, you won't be able to do it. So when you synthesize a new circuit, sometimes you go through different choices which may be incorrect, but finally you arrive at the correct one. So the principle here is negative feedback, and if Vi is greater than V0, V0 must be increased, and if Vi is less than V0, it must be pulled down, and so on. And how do we increase or decrease a voltage while using a current source? We have to push current into a node to increase its voltage and pull current out of a node to reduce its voltage. Okay. So let me redraw this. By the way, I am starting from the small signal picture of the transistor. Okay. So when we want to realize a functionality such as the voltage controlled voltage source, we want to realize some functionality which is a linear function. V0 is k times Vi, or V0 equals Vi, and so on. So that we synthesize using the small signal picture of the MOS transistor. Now we know a number of ways of biasing the transistor, and we can choose any one of them to go with the functional small signal equivalent circuit to come up with the complete circuit. So in every one of these cases, the functional synthesis is done in the small signal domain, the incremental domain, and you add an appropriate biasing arrangement. You will find that some types of biasing arrangements are more convenient than others, and you use the most convenient one. Okay. So again, what I did was apply the input to the gate. Okay. And the source node here, this will be the output voltage. If I do that, obviously the gate source voltage will be equal to Vi minus V0. We knew that between the gate and source we have to have either Vi minus V0 or V0 minus Vi, so that we effectively are comparing the input and output voltages. So in this case, it's Vi minus V0. Now we already designated the source as the output node, and let's see if it will be consistent. Now the drain I have not connected anywhere, so let me connect it to the small signal ground. Now what happens if Vi is more than V0? Okay, that is V0 is smaller than what is required, what is desired. Okay, Vi is more than V0, then current flows this way. Okay, and as before, remember, at the source there is only the current source. So you may be wondering how Kirchhoff's current law is satisfied, but as with other negative feedback circuits, you imagine a parasitic capacitor here, and this can be arbitrarily small. Okay, it doesn't matter how much it is. The point is, if current is pushed into this node, it goes into the capacitor, and V0 gradually increases. Okay, and this is exactly what you want, because here in this case V0 is smaller than what is required, so it will be increased. And exactly the opposite will happen if Vi is less than V0, then V0 is too high, and this current will be pointing upwards, right? It will be pulling current out of this node, and that will pull current out of the capacitor, and the output voltage will reduce. So this is consistent, and basically the small signal picture we want to have for the voltage buffer is just this. The drain can be connected to ground because we are not using it at all. The input is applied to the gate of the transistor. Okay, and at the output you can imagine a parasitic capacitor so that you can visualize this current going somewhere if Vi is different from V0, and the output V0 is taken from the source of the transistor. So this is all the circuit. Now clearly in this you can see that in steady state, this current here through this capacitor has to be 0. I mean, really nothing is connected to it as far as DC is concerned. So this current has to be 0. And how will this current be 0? This current can be 0 only if VGS is 0. And if VGS has to be 0, V0 has to be equal to Vi. The output and input voltages have to be exactly equal to each other. Okay. You are familiar with this type of arguments. First imagining that V0 is different from Vi, and then figuring out what happens. We did this while biasing the transistor at a constant current, and we are using the same thing again. And now you can see that there is only one possibility here. VGS has to be exactly equal to 0. Okay. I have now intuitively shown how this particular topology achieves V naught equals Vi, we will analyze this in the forthcoming lessons and see exactly how it behaves. Okay. So at least by now you should be convinced that V naught will be equal to Vi. Okay. Because V naught equals Vi, this has a gain K equals 1, and you can see whether it has desirable qualities of a voltage controlled voltage source. That is, the input resistance is infinity and output resistance is 0 and so on. At least one part of it, the input resistance, it's very easy to see. The input is connected to this. Okay, I have not shown the complete source, it's connected to the gate. The gate current is 0, so the input doesn't draw any current at all. Okay, so at least it must be clear from this picture that the input resistance is infinite. Okay, so that part is satisfied. So the other part, the output resistance, we will analyze in the forthcoming lessons. Okay.